Pick up a handful of sand. Go ahead, imagine it, feel the weight, the warmth, let it fall. Each grain is a year, a century, 1,000 years. The sand in your palm is the last 10,000 years of human civilization. Every empire, every monument, every god that was raised and forgotten, every language ever spoken. Now look at the beach, all of it. Every grain on every beach, on every coast, on every continent. That is the 4.5 billion years that came before the 10,000 years in your hand. And somewhere in that darkness, buried under layers of time so dense they crush the mind, something is waiting. A question that science almost forgot to ask. What if we are not the first? Not the first civilization. Not the first species to build, to burn, to reshape the surface of this world. Not the first intelligence to look up at the stars and wonder what it all means. What if the Earth has already seen our story and simply forgot? This sounds like science fiction. It sounds like the kind of claim made at 3 a.m. on a conspiracy website, not in the pages of a peer-reviewed academic journal. And yet, in 2018, two of the most credentialed scientists working in their fields, astrophysicist Adam Frank of the University of Rochester and climate scientist Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, published a paper in the International Journal of Astrobiology, a real journal, with peer review, with citations, with all the rigor that modern science demands. They called it the Silurian Hypothesis. And what they asked, formally, carefully, with full scientific seriousness, was this: if an industrial civilization had existed on Earth millions of years before our own, would we even be able to detect it? The name comes from a fictional species in the British science fiction series Doctor Who. Intelligent reptiles called Silurians, who supposedly built an advanced civilization during Earth's ancient past, long before the first humans walked African grasslands. Frank and Schmidt borrowed the name with a wink. They were not suggesting that reptiles built nuclear reactors. They were not endorsing any alternative history. They were asking something more precise, more unsettling, more scientifically honest. They were asking, what would the evidence look like? How long would it last? And how would we distinguish it from the noise of natural geological processes? To answer that question, we first have to understand the scale of the problem. Complex life has existed on this planet for at least 540 million years, since the Cambrian explosion, when the ocean suddenly filled with creatures of extraordinary variety. Land animals have walked the continents for nearly 400 million years. Dinosaurs alone dominated for 150 million years. 150 million years. Try to feel that number. If you counted one digit per second, 1, 2, 3, it would take you nearly 5 years to reach 150 million. The Tyrannosaurus rex lived closer in time to us than to the Stegosaurus. The late Cretaceous is separated from the late Jurassic by more time than separates us from the extinction event that ended the dinosaurs. Within that vast expanse of time, countless species lived and died that we know nothing about. The fossil record preserves perhaps 1% of all species that ever existed. The other 99% simply vanished, leaving no bones, no footprints, no chemical traces. And our own industrial civilization, the one that has produced factories and power plants and cities visible from orbit, is approximately 300 years old. 300 years out of 400 million. If you compressed the entire history of complex life on Earth into a single calendar year, with the Cambrian explosion on January 1st and tonight as midnight on December 31st, then the entire reign of the dinosaurs would occupy from May through October. Every human species that ever existed would appear in the final 12 minutes before midnight. Agriculture, cities, writing, the last 40 seconds. And everything we have built since the Industrial Revolution, every skyscraper, every power plant, every nuclear weapon, every satellite, every highway, every landfill, would fit inside the final quarter of a second before the clock strikes midnight. 1/4 of 1 second. Now ask yourself, in the 11 months, 29 days, 23 hours, 59 minutes, and 59 3/4 seconds that came before, are you absolutely certain nothing happened? Here is what paleontology can tell us with confidence. The conditions required to preserve organic material in stone are extraordinarily specific. An organism must die in the right environment, typically shallow water or a floodplain where sediment can rapidly cover the remains. It must be buried before scavengers and bacteria consume it. The sediment must have exactly the right mineral chemistry to replace organic tissue with stone. The resultant rock must survive subsequent erosion, burial, metamorphism, tectonic activity, and subduction, and the fossil must eventually be exposed at the surface precisely where a paleontologist happens to look. Each of those conditions is improbable. All of them together are vanishingly rare. Scientists estimate we have fossil evidence of roughly 1% of all species that have ever lived. Some estimates put it lower. The vast majority of life that has ever existed on this planet left no record whatsoever. They lived. They died. They disappeared. This is not a flaw in the geological record. It is the nature of how rocks work. And it is the foundational problem with any claim, in either direction, about what may or may not have existed before us. We find what we look for, and for most of the history of science, we have not been looking for this. Adam Frank has spent his career thinking about civilizations, not just ours, but the ones that might exist across the universe. His research into stellar evolution and the conditions for life led him inevitably toward a question that the scientific establishment rarely asks directly. How common is technological civilization? How long do civilizations typically last? What happens to a planet when intelligence emerges? Gavin Schmidt has spent his career staring at the Earth itself, specifically at the thin layers of sediment and ice that record the planet's climate history. He understands better than almost anyone alive how Earth's chemical systems respond to perturbation, how carbon moves between atmosphere and ocean and rock, how temperature signals are preserved across millions of years. Together, they approached the Silurian Hypothesis not as science fiction enthusiasts, not as conspiracy theorists, but as specialists in exactly the right fields to ask it properly. Frank brought the cosmological perspective, what civilizations do to planets. Schmidt brought the geological toolkit, what we would expect to find, and how long it would survive. What they found when they looked carefully was not evidence of a previous civilization. It was something subtler and in some ways more troubling, They found that we would probably not be able to tell the difference. So let us follow their logic into the deep past. Let us follow the evidence down through layers of rock and time, through the geological eraser that has been running for 4.5 billion years, and ask what, if anything, could possibly survive. Because before we can ask whether a previous civilization existed, we need to understand what the Earth does to evidence. The answer is going to be uncomfortable. Imagine that tomorrow, at exactly noon, every human being on Earth simply stops existing. No war, no plague, no catastrophe. We are here, and then we are not. 7 billion people vanished. Every city suddenly empty. Every engine stopped. Every screen gone dark. What happens next? This is not a thought experiment about human psychology or social collapse. We will not follow the survivors because there are no survivors. This is a forensic exercise. We are going to watch what happens to the evidence of our existence, not over years, not over centuries, but over geological time. We are going to watch the Earth erase us. Within hours, the power grid fails across most of the world. Nuclear plants, lacking operators to manage them, begin controlled or uncontrolled shutdowns. Some melt down. Fires break out in chemical plants, refineries, laboratories. Lightning strikes empty buildings with no fire crews to respond. Within weeks, vegetation begins its counterattack. Grass pushes through hairline cracks in pavement. Vines find purchase on glass and steel. Tree seedlings that had been growing in gutters and corners, suppressed by maintenance crews, are suddenly free. Within decades, most wooden structures collapse. Termites rot, weather. Houses in temperate climates become rubble within 50 years. The great glass towers of modern cities begin to show their age. Windows failing, steel supports weakening as rust spreads through expansion joints. Within 2 or 3 centuries, virtually every above-ground human structure has been reduced to ruins. The exceptions: massive stone constructions in dry climates, the Egyptian pyramids, the temples of Petra, the Great Walls of China. These survive, but even they are being slowly consumed by time. 500 years, the ruins themselves are mostly buried. Cities become mounds, the same kind of mounds archaeologists dig into today. The signature of civilization is already becoming geological. Now, we accelerate. 10,000 years after the last human, the cities of New York, London, Tokyo, buried under meters of sediment. The skeletons of skyscrapers have collapsed, crushed, redistributed. River deltas have shifted. Coastlines have changed. Glaciers, if the climate has cooled, have ground everything beneath them into powder. 1 million years. Virtually nothing recognizable remains on any surface. The geology has reasserted complete dominance. Any exposed concrete or steel has been weathered to its mineral components and dispersed. The great landfills have been buried, compressed, altered. 10 million years. The sedimentary record of our existence is now a layer, perhaps a few centimeters thick, compressed into rock. The chemical signatures of our activity are fading. 50 million years. The layer is compressed to millimeters. The chemical signatures have been substantially altered by heat, pressure, and the chemical activity of fluids moving through rock. 100 million years. Most of what we were has vanished into the noise of natural geology. The process responsible for most of this erasure is one we tend to think of as neutral background, the movement of tectonic plates. But plate tectonics is not background. It is the most powerful geological force on the planet, and it operates as a continuous, relentless recycling system. The Earth's surface is divided into roughly 15 major plates and dozens of smaller ones. These plates float on a layer of semi-molten rock called the asthenosphere, and they move slowly on human timescales, but with absolute certainty across geological time. A few centimeters per year. Over 1 million years, that becomes tens of kilometers. Over tens of millions of years, it becomes thousands. Where plates collide at ocean-continent boundaries, the denser oceanic crust is forced downward, subducted beneath the lighter continental crust. It descends into the mantle, where temperatures exceed 1,000 degrees Celsius. Everything on it, every sediment, every fossil, every artifact, every chemical trace, is carried down into that heat and destroyed, melted, homogenized, recycled into fresh rock that may eventually resurface through volcanoes. No oceanic crust older than approximately 200 million years exists anywhere on Earth today. Everything older has been subducted. The entire history of everything that ever rested on the ocean floor before 200 million years ago is simply gone. Continental crust is more durable. It is less dense, so it tends to float and survive. This is why some continental rocks are 4 billion years old. But even continental crust does not preserve evidence cleanly. Continents collide and mountains rise. Mountains erode, and material is carried to the sea, where it may eventually be subducted. Rock is buried, heated, pressurized, metamorphosed beyond recognition. The Earth's crust is not a museum. It is a furnace with a conveyor belt. While plate tectonics operates on the grand scale, erosion works at the surface, grain by grain, over timescales that are immense but comprehensible. The Grand Canyon is carved through more than 1 mile of rock, limestone, sandstone, shale, granite, by the Colorado River over approximately 5 to 6 million years. 5 to 6 million years of water carrying away rock, grain by grain, molecule by molecule. That same process applies to everything on Earth's surface. The Appalachian Mountains, which once rivaled the Himalayas in height, have been reduced to gentle ridges by hundreds of millions of years of rain and rivers and frost. The limestone rock of the English Cotswolds was once living coral reef at the bottom of a warm, shallow sea. Imagine a city. Stone foundations, steel frames, glass towers, concrete roads. Now imagine rain. Not the rain of a single storm, but 4 million years of rain. The mechanical force of water freezing in cracks and prying rock apart. The chemical dissolution of limestone by slightly acidic rainwater. The biological activity of roots and microbes breaking stone into soil. Now imagine 4 million years of that, plus rivers carrying the fragments to the sea, plus periodic burial under glacial deposits, plus the organic acids produced by 5 million years of decomposing plant matter. By then, the city does not exist, not in any form that could be recognized as a city. Not in any form that would suggest intelligence to a geologist examining the rock. What might survive are chemical anomalies, disruptions in isotope ratios, unusual concentrations of elements, traces not of civilization itself, but of what civilization did to the chemistry of the environment around it. And this is where the thought experiment becomes genuinely interesting. Different signatures of industrial civilization decay at different rates. Understanding which ones might survive millions of years and which would be indistinguishable from natural processes is the core intellectual challenge of the Silurian Hypothesis. Physical artifacts, essentially zero survival after 10 million years. Stone tools, which are our oldest evidence of human technology, survive in recognizable form for millions of years, but only as isolated fragments and only in favorable sedimentary environments. Metal objects corrode and disperse. Concrete dissolves and recrystallizes into minerals that look entirely natural. Glass weathers and loses its distinctive properties. The built environment leaves no recognizable trace. Radioactive isotopes, moderate survival depending on half-life. The nuclear weapons tests of the mid-20th century scattered isotopes like plutonium-239 and cesium-137 across the entire planet. Plutonium-239 has a half-life of 24,000 years, already gone in the deep geological sense, though its decay products would leave anomalies for somewhat longer. Longer-lived isotopes would create detectable signals for millions of years. A previous civilization with nuclear technology would leave an isotopic fingerprint in sediment records, though that fingerprint would overlap with natural isotope anomalies from cosmic ray bombardment and natural uranium deposits. Carbon isotope ratios, high survival potential, millions to tens of millions of years. Organic carbon, the carbon in coal, in oil, in all ancient biological matter, contains less carbon-13 than inorganic carbon. When an industrial civilization burns fossil fuels, it shifts the ratio of carbon isotopes in the atmosphere, oceans, and eventually in the sediment record. This shift is already detectable in ice cores and marine sediment cores from our current era, beginning around 1750 and accelerating dramatically through the 20th century. A similar signal from a previous industrial civilization could persist, compressed and distorted, but potentially detectable, for tens of millions of years. Mass extinction, very high survival potential, hundreds of millions of years. The rapid disappearance of species produces a recognizable pattern in the fossil record. A sudden collapse in diversity followed by the expansion of generalist opportunists. We can read mass extinctions from hundreds of millions of years ago. A technologically caused extinction would look like what we are currently causing: a rapid, global, apparently non-climatically triggered biodiversity collapse. Whether it would be distinguishable from a climate-triggered or impact-triggered extinction is the question. Synthetic materials, uncertain survival. Plastics break down, but may leave persistent organic traces. Certain industrial chemicals are extraordinarily stable and could survive in sediment for millions of years, though whether they would be identifiable as synthetic rather than products of unusual natural chemistry is unclear. Here is a useful comparison. The fossil record of our own species is extraordinarily sparse. Homo sapiens has existed for roughly 300,000 years. For most of that time, we were nomadic hunter-gatherers, living in small bands, leaving almost no durable trace. Our bones are rare in the fossil record. Our tools, stone, the most durable material available, are found scattered across continents in small numbers, often in isolation. If you wanted to find evidence that Homo sapiens existed 100,000 years ago, from the sediment record alone, you would be working with bone fragments and isolated stone tools, separated by thousands of kilometers, buried under meters of sediment. Rare enough that many sites have not been discovered in 150 years of active archaeology. Now, extend that logic to a hypothetical species that existed 50 million years ago. Any physical artifacts would have had 50 times longer to be destroyed. The probability of finding even a single recognizable object, even if they produced millions of them, approaches zero. And this assumes they made objects like ours. This assumes they worked in stone or metal. What if they used entirely different materials? What if their technology left a different kind of trace, or a trace we have never thought to look for? We find what we look for. We look for what we expect to find. And for the last century and a half, we have not been looking for this. So the physical evidence is almost certainly gone. The cities have been crushed. The roads have dissolved. The satellites have long since deorbited and burned and scattered their atoms across continents. But what about the chemistry? What about the signals that are not made of stone or metal, but written in the ratios of invisible atoms, preserved in the pages of sediment that line the floors of ancient oceans? There is an event in Earth's history, an event that happened 56 million years ago, that looks uncomfortably familiar. That looks, in its chemical signature, in its global consequences, in its timeline, remarkably like what we are doing right now. Scientists have a name for it, and when you understand what it represents, what it looks like in the record, you will understand why the Silurian Hypothesis is not a fringe idea. It is a serious scientific question. 56 million years ago, the Earth was already a warm planet. The Arctic was ice-free. Temperate forests grew near the poles. Sea surface temperatures at high latitudes were warmer than anything in modern experience. The continents were in different positions. The Atlantic was narrower. India had not yet completed its collision with Asia. The world was recognizable in its basics, but alien in its details. And then, over a period of roughly 20,000 years, a geological instant, something happened. Massive quantities of carbon entered the atmosphere. Global average temperatures rose by 5 to 8 degrees Celsius. The Arctic Ocean reached surface temperatures of 23 degrees, comparable to modern subtropical seas. The deep oceans were stripped of oxygen. Many species of benthic foraminifera, tiny shelled organisms that live in the deep sea mud, went extinct. On land, the flora and fauna of North America shifted dramatically as subtropical conditions pushed northward. This event is called the Paleocene-Eocene Thermal Maximum, the PETM, and it is one of the most studied events in deep Earth history. It is also the event that, when Frank and Schmidt examined it carefully, they identified as the best natural test case for the Silurian Hypothesis. The evidence for the PETM comes from an extraordinary archive: sediment cores drilled from the floors of the world's oceans. These cores, extracted using ships equipped with drilling rigs that can penetrate kilometers of water, and then kilometers of sediment, are geological time capsules. Each centimeter of sediment represents thousands of years of ocean history, the shells of dead organisms, the chemical composition of the water in which they formed, the ratio of isotopes in their calcium carbonate, all of it preserved in layered sequence. When scientists examine the PETM horizon in these cores, they see several things simultaneously. First, a sharp negative excursion in the carbon isotope record. The ratio of carbon-13 to carbon-12 drops suddenly, a signature indicating that large quantities of carbon depleted in carbon-13 entered the system. Carbon from organic sources, ancient biological material, is depleted in carbon-13. This is the same signature we see today from burning fossil fuels. Second, a dissolution horizon. In the deep ocean, calcium carbonate dissolves when water becomes acidic. During the PETM, large areas of the deep ocean floor show a layer where carbonate has dissolved, evidence of ocean acidification on a global scale. Third, a warming signal. The oxygen isotope ratios in the shells of surface-dwelling organisms shift, indicating temperature rise. Foraminifera that lived in cold water are replaced by warm water species. Fourth, species turnover. In the deep ocean, approximately 50% of benthic foraminifera species disappeared. On land, the event is associated with the appearance of the first modern horse ancestors, smaller than their predecessors, a biological response to warmer conditions. The PETM lasted approximately 200,000 years before temperatures returned to near baseline. It was a global perturbation. Every ocean, every continent, every sediment record on Earth shows its signature. The leading explanations for the PETM are entirely natural, and they are supported by substantial evidence. The primary candidate is massive volcanic activity associated with the opening of the North Atlantic. As Greenland separated from Europe roughly 56 million years ago, vast quantities of magma intruded into seafloor sediments and coastal regions, forming what geologists call the North Atlantic Igneous Province. These eruptions, some of the largest in the last 100 million years, would have released enormous quantities of carbon dioxide into the atmosphere, triggering initial warming. That warming, in turn, may have destabilized methane hydrates on the continental shelves, ice-like structures that trap methane in sediment at cold temperatures and high pressures. As seafloor temperatures rose, the hydrates could have become unstable, releasing methane, a greenhouse gas approximately 80 times more potent than carbon dioxide over a 20-year period, into the water column and atmosphere. This would have amplified the warming in a self-reinforcing feedback loop. These are good explanations. They are physically plausible. They are supported by geological evidence from the North Atlantic. They are almost certainly what happened. But Frank and Schmidt made a careful observation. They noted that the carbon isotope signature of the PETM is anomalously depleted in carbon-13, even relative to what you would expect from pure volcanic eruption. The signal looks more like organic carbon, ancient biological material, than volcanic carbon. This is consistent with the methane hydrate hypothesis. But it is also consistent with one other possible source: fossil fuels. Here is the comparison that makes climate scientists uncomfortable, not because they believe it, but because of what it reveals about our methods. The PETM involved rapid carbon input to the atmosphere over roughly 20,000 years, a carbon isotope signature depleted in carbon-13, consistent with organic sources, global temperature rise of 5 to 8 degrees Celsius, ocean acidification sufficient to dissolve deep-sea carbonates, species extinction, particularly among marine organisms, significant disruption to terrestrial ecosystems. Our current situation involves rapid carbon input to the atmosphere, currently at a rate estimated to be 10 times faster than the PETM. The same carbon-13 depleted isotope signature. Because we are burning fossil fuels, ancient organic carbon. Projected temperature rise of 3 to 5 degrees Celsius by 2100, more if feedbacks accelerate. Ocean acidification already measurable in every ocean on Earth. A mass extinction currently underway, with species loss rates 100 to 1,000 times the natural background rate. The signatures are similar. The mechanism is the same. Rapid injection of organic carbon into the atmosphere. The consequences are analogous. If a future geologist or a future intelligent species examined the sediment record from our era 10 million years from now, they would see a carbon anomaly, a thin layer of depleted carbon-13, a dissolution horizon, an extinction event, a sharp disruption in the pattern of life. And they would look at the layer just below it, the pre-industrial Holocene, and see stable conditions, steady isotopes, diverse ecosystems. Then they would see our layer, disruption, spike, extinction, and they would write, in their equivalent of a scientific paper, that this was caused by volcanic activity, or a methane release, or some natural climate feedback, because that is what their methods would suggest, because their methods, like ours, would be calibrated to find natural explanations first, because extraordinary claims require extraordinary evidence, and the extraordinary claim, industrial civilization, would be the last hypothesis on the list. Frank and Schmidt were very clear about what they were and were not claiming. They were not claiming that the PETM was caused by a previous industrial civilization. They explicitly stated that they considered this unlikely. The natural volcanic explanation is compelling. The methane hydrate mechanism is well understood. There is no physical evidence, no synthetic compounds, no radioactive anomalies, no technofossils in PETM sediments. What they were claiming was something more subtle and more important, that the signatures of a previous industrial civilization in the geological record would look very similar to certain natural events, and that our standard methods for studying those natural events are not designed to look for industrial signatures. They proposed a simple test. Go back to the sediment cores from the PETM, run them through a different set of analyses. Look for synthetic organic compounds, molecules that cannot form naturally. Look for unusual heavy metal concentrations. Look for isotope anomalies that do not fit any natural model. If you find nothing, you have stronger evidence that the PETM was entirely natural. If you find something anomalous, something that requires explanation, then you have a mystery worth pursuing. To the best of current knowledge, this targeted analysis has not been done, not because scientists believe a previous civilization caused the PETM, but because the question has not been considered worth asking. which raises a question of its own. Science is not a collection of facts. Science is a method, a systematic approach to asking questions and testing answers. And like any method, it has blind spots. It is calibrated to find certain things and not others. It is optimized for natural explanations, because natural explanations are, in almost every case, correct. But the optimization itself is a kind of assumption. When we study the PETM, we ask, what volcanic mechanism could have caused this? What natural feedback? What orbital forcing? We do not ask, could this have been caused by intelligence? Not because intelligence is impossible, but because we assume it did not exist yet. That assumption is based on our best current understanding of evolutionary history, which suggests that intelligence of the kind required for industrial civilization was not present on Earth 56 million years ago. And that assumption is probably correct. But probably correct and certainly correct are different things. And the difference matters, not because we should believe a previous civilization existed, but because we should know how to look for evidence of one if we wanted to. And currently, we largely do not. The Silurian Hypothesis is not a claim. It is a diagnostic tool. It reveals the limits of our detection capabilities. It asks, what would we expect to find, and how confident are we that we would recognize it? The PETM is one data point in that diagnostic exercise. There are others. The PETM is the most dramatic, but it is not the only hyperthermal event in the geological record. The late Paleocene and early Eocene, the 50 million year period that included the PETM, were characterized by several smaller warming events, occurring in clusters separated by tens of thousands of years. The PETM2, or Eocene Thermal Maximum 2, occurred roughly 2 million years after the PETM and shows similar, though smaller, signatures. Similar events occur throughout the deep geological record. The Triassic-Jurassic boundary, approximately 200 million years ago, shows evidence of rapid carbon injection and warming associated with the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. The Permian-Triassic boundary, the Great Dying, the worst mass extinction in Earth's history, 252 million years ago, shows carbon anomalies, ocean acidification, and temperature excursions of similar signature to the PETM, though far larger in magnitude. All of these events have natural explanations. All of them are well studied. None of them have been analyzed with the specific methodology Frank and Schmidt propose. This does not mean previous civilizations caused them. It means we do not know whether any anomalous artificial signatures exist within them, because we have not looked. The absence of evidence, in this case, is not evidence of absence. It is evidence of absence of investigation. So the chemical record preserves some things for a very long time. Carbon isotope anomalies, ocean chemistry disruptions, mass extinction patterns. These are the ghost in the chemistry, the echoes of catastrophic events written in the ratios of invisible atoms. But Frank and Schmidt identified something even more specific. Something that our civilization is currently producing that would be genuinely unprecedented in the geological record. Something that, if found in ancient sediment, could not be explained by any volcanic mechanism or natural feedback. something called a technofossil. And the question of what a technofossil is and how long it might survive takes us into territory that is simultaneously more concrete and more philosophically disturbing than anything we have covered so far. There is a word that geologists coined only recently, a word that did not need to exist until our current civilization made it necessary. Technofossil. A technofossil is any manufactured object or material that, when incorporated into the geological record, has no natural analog, something that could not have been produced by any known natural process, something that says, unambiguously, intelligence was here. Fossils, in the conventional sense, are the preserved remains of living organisms. A technofossil is the preserved remain of a civilization's products. A brick, a polymer, a radioactive isotope released by nuclear fission, aluminum in pure metallic form, a synthetic molecule that could not assemble itself without directed chemistry. We are producing technofossils right now, in quantities that will be detectable in the geological record for millions of years. The question the Silurian Hypothesis asks is, if we found them in the record of a previous era, would we recognize them for what they are? Plastic is the most visible technofossil of our civilization. We produce approximately 400 million metric tons of plastic annually. We have produced a total mass of plastic since the mid-20th century that exceeds the mass of all living marine mammals. Much of it ends up in the environment, in landfills, in rivers, in the ocean, in agricultural soil, in Arctic snow, in the bodies of animals at every level of every food chain on Earth. Microplastics, fragments smaller than 5 millimeters, created by the breakdown of larger plastic objects, have been found in the deepest ocean trenches. At 36,000 feet below the surface, they have been found in the snow on the summit of Mont Blanc. They have been found in the bloodstream of freshwater fish in remote mountain streams far from any industrial activity. Plastic does not biodegrade, not in any ecologically meaningful time frame. It photodegrades under ultraviolet light, breaking into smaller and smaller fragments. But the polymer chains themselves persist. The fundamental chemical structure remains. How long do plastics persist in the geological record? This is uncertain. Complex polymer chains will eventually break down under the combined action of heat, pressure, UV radiation, and chemical attack. Over millions of years, most current plastics would be reduced to simpler organic compounds. Whether those compounds would retain any identifiable relationship to their original synthetic nature is unclear, but the layer will be there. A stratum in the sedimentary record of the mid to late 20th century and beyond, globally distributed across marine and terrestrial deposits, characterized by an unusual concentration of persistent organic polymers unlike anything produced by natural chemistry. That stratum, if it survives, is unambiguous. There is nothing natural that produces it. Only intelligence makes plastic. Here is something almost no one knows. Before the late 19th century, pure aluminum metal was extraordinarily rare on Earth, more expensive than gold. Napoleon III served his most honored guests with aluminum cutlery. Gold was reserved for lesser guests. The capstone of the Washington Monument, emplaced in 1884, was made of pure aluminum as a symbol of ultimate prestige. Aluminum is the most abundant metal in the Earth's crust, locked into aluminum silicate minerals, feldspar, clay, bauxite. But extracting pure aluminum from these minerals requires enormous quantities of electricity. In nature, this never happens. Elemental aluminum essentially does not occur naturally on Earth's surface. Since the invention of the Hall-Héroult electrolytic process in 1886, we have produced over 1 billion metric tons of aluminum. We produce 65 million metric tons annually. Aluminum artifacts incorporated into marine sediment or lake deposits would represent an isotopic and chemical anomaly with no natural explanation. Pure metallic aluminum, or its oxidation products in unusual form in a sedimentary context. A geologist 50 million years from now, examining sediment from our era, would find aluminum anomalies. They might be subtle. Weathering and diagenesis would alter the form of the metal significantly, but the anomaly would be there and it would require explanation. Between 1945 and 1963, the major nuclear powers conducted above-ground weapons tests. Approximately 500 nuclear detonations released an inventory of radioactive isotopes into the global atmosphere. These isotopes, including plutonium-239, cesium-137, strontium-90, and dozens of others, were distributed worldwide by atmospheric circulation, settling into sediment everywhere. This radioactive layer is one of the proposed golden spikes for the beginning of the Anthropocene, the proposed new geological epoch defined by human impact. Sediment cores from every ocean, every lake, every river delta on Earth show the same abrupt increase in certain radionuclides beginning in the early 1950s. The persistence of this signal varies by isotope. Cesium-137 has a half-life of 30 years, already largely gone. Plutonium-239 has a half-life of 24,000 years, still significant, but geologically ephemeral. Plutonium-240, which decays more slowly, would leave traces for longer. The decay products of all these isotopes and the anomalous isotope ratios they create could potentially be detected in sediment for millions of years with sufficiently sensitive instruments. But here is the critical caveat. Radioactive anomalies can be produced by natural processes. Cosmic ray bombardment creates certain radionuclides in the atmosphere and on rock surfaces. Natural uranium deposits undergo spontaneous fission. Volcanic activity releases naturally occurring radioactive materials. The question is whether an artificial nuclear event, weapons testing, reactor operation, nuclear industrial activity, produces a signature distinguishable from natural isotope anomalies. And here, a remarkable geological discovery becomes relevant. In 1972, French nuclear scientists analyzing uranium ore from a mine in Oklo, Gabon, in Central Africa made a startling discovery. The uranium in this ore was anomalously depleted in uranium-235, the fissile isotope used in nuclear weapons and reactors. The ore had already been used as nuclear fuel, and it had been used approximately 2 billion years ago. At Oklo, a unique set of geological conditions conspired to create a natural nuclear fission reactor. The uranium ore was unusually concentrated. The rock formation was saturated with water, which acted as a moderator to slow neutrons, and sustain the chain reaction. Approximately 16 separate zones underwent sustained fission reactions over periods of hundreds of thousands of years, producing energy, heat, and a full inventory of fission products. The Oklo reactors are now extinct. The uranium-235 has been too depleted to sustain reaction, but their products remain: anomalous concentrations of rare isotopes, unusual patterns of rare earth elements, the distinctive chemical signature of fission reactions. Scientists have mapped the reactor zones in detail and understand them thoroughly. The Oklo reactors are important for the Silurian hypothesis for this reason. They demonstrate that natural nuclear events can produce isotopic signatures that could, in principle, be confused with artificial nuclear activity. A future geologist, or even our current geologists if the context were not known, might initially interpret Oklo as the site of ancient industrial activity. Conversely, an industrial nuclear event buried in the record without its context might be interpreted as natural. This is not to say that distinguishing between natural and artificial nuclear events is impossible. The isotope ratios are different. The spatial distribution is different. The associated chemical signatures are different. But it requires knowledge of what artificial nuclear activity looks like. And it requires investigating with that hypothesis in mind. The strongest argument against the existence of any previous industrial civilization is straightforward, and it deserves to be taken seriously. When we began industrializing in the 18th century, we found an abundance of easily accessible fossil fuels, coal seams near the surface, oil deposits that could be reached with relatively primitive drilling technology, natural gas associated with easily located formations. These resources had accumulated over hundreds of millions of years, undisturbed. If a previous industrial civilization had existed and followed any trajectory similar to ours, using fossil carbon as an energy source, we would expect to find these resources significantly depleted. The fact that they were waiting for us, undisturbed, when concentrations accessible to early industrial technology, suggests strongly that no one extracted them before. This argument is powerful, and Frank and Schmidt acknowledge it, but it has limits. A civilization that arose before the Carboniferous period, before the great forests of the Carboniferous, whose remains became coal, would have had no coal to burn. Carboniferous coal deposits are between 300 and 360 million years old. A civilization that existed 400 million years ago would have been dealing with a very different geological and biological landscape, with different available resources. Similarly, a civilization that developed along different technological pathways, using nuclear power or geothermal energy, or forms of energy storage that do not require organic carbon combustion, might have left fossil fuel deposits completely untouched, and a civilization sophisticated enough to develop any of these alternatives would, presumably, leave different signatures than we do. Signatures we might not be looking for. So the technofossil record is real. The chemical signatures are real. The radioactive layer is real. These are the ways our civilization will write itself into stone, and the ways a previous civilization might have done the same. But there is another dimension to this problem that is older than chemistry, older than geology. It is encoded not in rock, but in the oldest thing humans carry with them: memory. across every culture, on every continent, in every era of recorded human history, before our writing, before our science, before our ability to drill into the seafloor and read 400 million years of climate history, there are stories about something that was before, something that was lost, something that came before us and passed away. Why are these stories everywhere? What do they mean? And is there any possibility, any scientific possibility at all, that they contain a fragment of something real? Southeastern Turkey. The year is 1994. A Kurdish farmer turns over the soil with his plow, and his blade strikes something hard. He looks down and sees carved stone. He assumes it is a grave marker and alerts authorities. A German archaeologist named Klaus Schmidt comes to look. Schmidt sees immediately what the earlier survey team that had dismissed the site in 1963 had failed to understand. The carved stones are not grave markers. They are worked in a way that suggests something far more significant. He begins to excavate. What emerges from the soil over the following years of careful excavation defies everything the scientific community thought it knew about the origins of civilization. Massive circular enclosures, T-shaped limestone pillars, some standing over 5 meters tall and weighing 50 tons. The pillars carved with intricate reliefs, lions, bulls, foxes, snakes, scorpions, vultures, spiders, cranes, and human hands. The carving sophisticated, stylized, deliberate, not the crude marks of beginners, but the work of a tradition that had mastered its craft. The oldest structures at Göbekli Tepe were built approximately 11,600 years ago. They predate Stonehenge by more than 6,000 years. They predate the Egyptian pyramids by more than 7,000 years. They are, currently, the oldest known monumental structures on Earth, and they were built by hunter-gatherers. This single fact has not been fully absorbed by the general public, but its implications are seismic for how we understand our own past. The standard model of cultural development, built over more than a century of archaeological and anthropological research, runs as follows. Humans hunt and gather. At some point, humans discover agriculture. Agriculture creates food surpluses. Surpluses allow specialization. Specialization creates social hierarchies, religions, administrators, artisans. These developments, over time, give rise to cities, writing, monuments, and what we recognize as civilization. Göbekli Tepe inverts this sequence. There is no evidence of agriculture at the site. No granaries, no domesticated plant remains, no animal pens. The people who built these structures were nomadic or semi-nomadic hunter-gatherers who relied on wild game and foraged plants. There are no houses, no permanent residential structures. Göbekli Tepe was not a city. It was a ritual center, a place of gathering, ceremony, feasting, and presumably shared belief. The animal bones found in enormous quantities at the site, primarily wild aurochs and gazelle, show evidence of large-scale butchering and cooking. These were feasts, feeding gatherings far larger than any individual band could sustain. People came from across the region. They coordinated, they planned, they built together, and then they built more. The excavation also revealed something about intentional forgetting. Around 10,000 years ago, After roughly 2,000 years of active use, the enclosures at Göbekli Tepe were deliberately filled in. Not abandoned, deliberately buried under thousands of tons of earth and rubble. The people who did this carried and deposited enormous quantities of material to cover what they had built. Why? We do not know. The people who built Göbekli Tepe left no written records. Their descendants forgot it existed. For 9,000 years, the site lay undisturbed, covered, waiting. Klaus Schmidt, who excavated it until his death in 2014, believed he had barely scratched the surface. Only a small percentage of the site had been excavated. He believed, and subsequent survey has confirmed, that there are structures beneath the hillside that are significantly older than those yet exposed. Göbekli Tepe is not evidence of a lost high civilization. The people who built it did not have metallurgy, writing, cities, or industrial technology. They were hunter-gatherers who achieved something remarkable within the constraints of their world, a monument to the capacity for collective action and shared belief that was present in human beings tens of thousands of years before what we usually call civilization. But Göbekli Tepe teaches something more important than its own history. It teaches us the shape of forgetting. Here was a massive, elaborately constructed architectural complex, the largest known from its era by far, that was deliberately buried and then forgotten so completely that it lay unrecognized for 9,000 years. Farmers walked over it. Shepherds grazed their flocks on the hillside above it. A survey team examined the broken stones visible at the surface and concluded it was an unimportant medieval cemetery. A decade and a half later, a more careful observer looked at the same stones and saw something completely different. If this could be forgotten, a structure of 50-ton carved limestone pillars constructed by hundreds of people over multiple generations in a region that has been continuously inhabited for thousands of years, what might have been forgotten from deeper in the past? What evidence might exist beneath our feet, unrecognized, waiting for someone to look at it differently? 12,800 years ago, the Earth was warming. The great ice sheets of the last glacial maximum were retreating. Sea levels were rising. Forests were spreading northward. The Ice Age was ending, and a new world was being born. Then, within perhaps a single decade, possibly less, temperatures in the northern hemisphere plunged. In Greenland, and the temperature dropped by an estimated 10 to 14 degrees Celsius in less time than it would take to write a doctoral thesis. The warming stopped. Ice sheets stabilized or began re-advancing. The transition to the modern interglacial, which had seemed inevitable, was interrupted for approximately 1,200 years. This cold period is called the Younger Dryas, named for a small Arctic flower, Dryas octopetala, that reappeared in regions where it had not grown for millennia. It ended as abruptly as it began, around 11,700 years ago, when temperatures in Greenland rose by 10 degrees in fewer than 50 years. The mainstream explanation for the Younger Dryas involves ocean circulation. As the ice sheets melted, enormous quantities of cold, fresh water poured into the North Atlantic, disrupting the thermohaline circulation, the system of ocean currents that distributes heat from the tropics to higher latitudes. Without this oceanic heat pump, temperatures plummeted. When the fresh water pulse ended, circulation resumed, and warming recommenced. This explanation has good support. Climate models can reproduce the Younger Dryas when they include a large freshwater forcing. Sediment cores show chemical changes consistent with altered ocean circulation. The timing corresponds with the catastrophic drainage of glacial lakes. But since 2007, a competing hypothesis has generated significant scientific controversy. A group of researchers proposed that the Younger Dryas was triggered, or at least precipitated, by a cosmic impact. A comet or asteroid, or perhaps multiple fragments of a disintegrating comet, they argue, struck Earth approximately 12,900 years ago. The evidence for the Younger Dryas impact hypothesis has been debated, attacked, defended, partially retracted, and revised through dozens of peer-reviewed papers over more than 15 years. The scientific community remains genuinely divided. The proponents point to a distinctive layer in sediment at hundreds of sites across North America, parts of Europe, the Middle East, and South America, a layer corresponding to the onset of the Younger Dryas. This layer contains materials they argue are consistent with a cosmic impact, microscopic glass spherules that appear to have formed at extreme temperatures, nanodiamonds, which form under intense pressure, elevated concentrations of platinum and iridium, elements common in meteorites but rare on Earth's surface, shocked quartz bearing the pressure fractures of a high-velocity impact. Critics have challenged each of these findings in detail, questioning the dating of the layers, proposing alternative natural origins for the proposed impact markers, and pointing to failures to replicate some results. Multiple attempts to replicate the spheral findings have produced mixed results. The debate continues, but in 2023 and 2024, new evidence emerged from marine sediment cores, an environment distinct from the primarily terrestrial sites examined previously. Researchers reported finding impact-consistent materials in cores from the North Atlantic and from a lake in South America, adding independent lines of evidence that some proponents argue cannot be explained by the same set of contamination or dating concerns raised against earlier work. The scientific jury is still deliberating, but the hypothesis has not been falsified, and it continues to attract serious researchers. What matters for our inquiry is not which hypothesis is correct, but what either scenario implies about the fragility of human civilization and memory. At the time of the Younger Dryas, humans had been in North America for at least 1,000 years, and possibly much longer. Some evidence suggests initial entry as far back as 20,000 or more years ago, far earlier than the Clovis culture that was long considered the first American inhabitants. Across Eurasia and Australia, sophisticated human populations had existed for tens of thousands of years. The evidence from sites like Abu Huraira in Syria suggests that people were beginning to experiment with plant cultivation just before the Younger Dryas began. Pre-agricultural villages or proto-agricultural settlements may have been developing in multiple regions. Then the cold came. Food sources shifted or disappeared. In North America, the megafauna that hunter-gatherers had relied upon, mammoths, mastodons, giant ground sloths, horses, went extinct within a relatively short time span. Whether climate, human hunting, or a cosmic impact was the primary driver of these extinctions, the result was the same. The ecological foundation supporting large human populations collapsed. Populations crashed. Cultures were disrupted. The social structures that allow knowledge to be transmitted from generation to generation. The apprenticeships. The storytelling traditions, the ritual practices that encode ecological knowledge in ceremony, were broken. Survivors rebuilt from fragments. This is not a speculative scenario. Archaeologically, we can see the disruption. The Clovis culture, the first clearly documented technological tradition in the Americas, disappears from the record at almost exactly the onset of the Younger Dryas and is replaced by different, regionally distinct cultural traditions during the subsequent millennia. Something broke the continuity. Now ask, if cultures that had existed for thousands of years could be disrupted and largely erased in a single cold millennium, what happened to the knowledge, stories, and technologies of all the human populations that preceded them over the previous 200,000 years? The flood myth is, after the creation narrative, the most widespread story in human culture. It appears in virtually every mythology on Earth. The Book of Genesis gives us Noah. Greek mythology gives us Deucalion and Pyrrha, who survive a great flood sent by Zeus. Hindu scripture describes Manu, who was warned by a divine fish and built a great boat. The Epic of Gilgamesh, the world's oldest written narrative, 3,000 years older than Genesis, gives us Utnapishtim, who receives the same warning and builds the same boat. Chinese mythology tells of the Great Flood that the engineer Gun and his son Yu spent decades trying to control. Aboriginal Australian oral traditions describe coastal features, islands, bays, headlands, that have been underwater for more than 7,000 years. These stories do not reference places that existed in any living person's memory. They are memories of a landscape that was flooded at the end of the last ice age. This is the scientific explanation for the persistence of flood myths. They are memories, not memories of a single global flood. There was no single event that flooded the entire world simultaneously, but memories of real, catastrophic flooding experienced by coastal and riverine populations as sea levels rose 100 meters over the 10,000 years following the last ice age. The flooding was not uniformly slow. There were periods of rapid rise, meltwater pulses, when glacial lakes burst through ice dams and released enormous volumes of water in geologically brief time spans. The flooding of what is now the Persian Gulf. The possible flooding of the Black Sea Basin as the Mediterranean breached the Bosphorus. The inundation of Doggerland, the landscape connecting Britain to continental Europe that was home to tens of thousands of people over thousands of years. These events happened. Populations were displaced. Survivors carried stories. Over generations, the stories were encoded in mythology. Specific landscapes transformed into universal archetypes, historical figures into divine protagonists, natural disasters into divine punishment. The myths preserve something real, not the scale they claim, not the supernatural framework in which they are embedded, but the core event. An earlier world, submerged, lost, a time before. A world we did not inherit, only remember in fragments. Atlantis needs to be addressed directly, because it will come up. Plato wrote about Atlantis in two dialogues, Timaeus and Critias, Composed around 360 BCE, he describes an island empire larger than Libya and Asia combined, located beyond the Pillars of Hercules, the Strait of Gibraltar, that was destroyed in a single day and night of earthquakes and floods, sinking beneath the waves 9,000 years before his own time. There is no mention of Atlantis in any source before Plato. None. Not in Egyptian records, which Plato claims as his source. Not in Mesopotamian texts. Not in any of the extensive records of Bronze Age Mediterranean civilizations. Not in the extensive Greek tradition that preceded Plato by centuries. Most classical scholars agree that Plato invented Atlantis as a philosophical and political allegory, a story about hubris, the corruption of power, and the inevitable fall of arrogant civilizations. It served his didactic purpose perfectly, a rich, powerful, technologically advanced civilization that grew corrupt and was destroyed by the gods. The story has been assigned to hundreds of proposed real locations: the Azores, the Canary Islands, Santorini, the Bahamas, the coast of Spain, Scandinavia, Antarctica. None of these proposals has withstood serious geological or archaeological scrutiny. The Atlantic Ocean floor is entirely oceanic crust. There is no mechanism by which a continent could have sunk there in the last 12,000 years and left no geological trace. Atlantis is not evidence of anything except the human need to believe in a lost golden age. It tells us about psychology, not history. But, and this is critical, the persistence of Atlantis as a cultural phenomenon and the widespread existence of genuine flood memories in mythology point to something real. Human beings throughout history have sensed that there is more to the past than they remember, that civilizations, or at least complex organized societies, rise and fall. That knowledge is lost, that the world they inherited is not the only world that has ever been. This intuition is correct. It is just not the way most people imagine it to be. Human memory, in the deepest sense, the collective memory encoded in language, in oral tradition, in the structures of culture and society, reaches back perhaps 10 to 20,000 years. No further. The deliberate burial of Göbekli Tepe approximately 10,000 years ago ensured that even relatively recent achievements could be completely forgotten. The Younger Dryas demonstrated that catastrophe can erase centuries of accumulated knowledge in a generation. Beyond the edge of human memory, we are dependent entirely on material evidence, fossils, artifacts, chemical signatures in sediment, isotope ratios in ice cores, and as we have seen, that material evidence is subject to the relentless erasure that the Earth performs on everything its surface has ever held. The deep human past, the 290,000 years of Homo sapiens history before Göbekli Tepe, is nearly silent. We have scattered stone tools, a few burials, cave paintings of extraordinary beauty, and minimal contextual information. We have almost no idea what those people knew, believed, experienced, or passed on to their children. And that is just our own species over a span of 300,000 years. What might have existed before us? What might have existed during the hundreds of millions of years when complex, intelligent, potentially curious life could theoretically have evolved on this planet? The edge of memory is a cliff, and beyond it, the past falls into a darkness that is not empty, only silent. We have been asking throughout this entire inquiry whether something came before us, whether the silence in the ancient record reflects the absence of civilization or merely its erasure. But there is a question we have been approaching from the beginning that we have not yet confronted directly. Not what came before us, but what are we leaving behind? What story will the rocks tell about us millions of years from now? What will the geologists of the far future, whatever they are, wherever they come from, read in the thin layer of sediment that marks our passage? And once we understand what we are actually writing into stone, the question of whether we are the first civilization begins to feel less like an academic puzzle and more like a warning. In 2016, the Anthropocene Working Group, a body of scientists convened by the International Commission on Stratigraphy, the organization responsible for dividing Earth's history into its official geological periods, voted to recommend that the Anthropocene be formally recognized as a new geological epoch. The Anthropocene, the age of humans. The proposal was not politically motivated, though it has political implications. It was a geological assessment. The scientists examined the evidence and concluded that human activity has so profoundly altered the Earth system in ways that will be preserved in the rock record for millions of years, that a new named epoch is scientifically justified. What would mark its beginning? Multiple candidates were proposed. The nuclear weapons tests of the 1950s, which created the global radioactive layer, now detectable in sediment everywhere. The mid-20th century acceleration of human industrial and agricultural activity, the Great Acceleration, during which the pace of change in virtually every human environment metric began to increase exponentially. The explosive dispersal of plastics, nitrogen compounds, novel chemicals, and heavy metals that define the chemical fingerprint of the modern era. The proposal is still under formal review, but the science behind it is not in dispute. We have changed the planet. We are changing it measurably, rapidly, globally, and the changes we are making will outlast us by millions of years. We are writing ourselves into the geological record right now. The question is what the record will say. Since the beginning of the Industrial Revolution, approximately 1850, human combustion of fossil fuels has released roughly 1,600 billion kilograms of carbon dioxide into the atmosphere, 1.6 trillion metric tons. The atmospheric concentration of carbon dioxide has risen from approximately 280 parts per million in the pre-industrial era to over 420 parts per million today, higher than at any point in the last 3 million years, and possibly the last 15 million. This carbon has a distinctive isotopic signature. Fossil fuels formed from organic matter that grew hundreds of millions of years ago. That organic matter was depleted in carbon-13, the heavier stable isotope of carbon, relative to the atmosphere. When we burn these fuels, we are injecting carbon-13 depleted carbon into the modern atmosphere and oceans. The ratio of carbon-12 to carbon-13 in atmospheric carbon dioxide and in the organisms that incorporate it and in the sediment that preserves them is shifting in a measurable and unprecedented way. This shift is already detectable in ice cores drilled from Greenland and Antarctica, in the shells of marine organisms, in the growth rings of ancient trees. It is called the Suez effect, after the scientist who first described it in the 1950s. 50 million years from now, a geologist examining marine sediment from our era will find this signal. They will see a sharp negative excursion in the carbon isotope record, beginning gradually around 1850 and accelerating dramatically in the 20th century. The excursion will be global, present in cores from every ocean. It will be correlated with other anomalies, a biodiversity collapse, unusual chemical signatures, the radioactive layer. They will recognize it as a significant perturbation event. They will search for its cause. Of all the marks we are leaving on the geological record, the most legible, and in some ways the most permanent, is the mass extinction we are currently causing. The term mass extinction has a precise technical meaning in paleontology: a rapid, global-scale collapse of biodiversity affecting a significant percentage of all species. The 5 previous mass extinctions in the history of complex life each appear in the fossil record as sharp boundaries, moments where the variety of species visible in the rock changes dramatically, with many forms disappearing and being replaced, after a gap, by new forms. We are currently causing a 6th mass extinction. This is not a political statement. It is a factual assessment based on decades of data from conservation biology, ecology, and paleontology. Species are currently going extinct at rates estimated to be 100 to 1,000 times the natural background rate, the rate of extinction that occurs in the absence of any unusual perturbation. The International Union for Conservation of Nature currently lists more than 40,000 species as threatened with extinction: amphibians, birds, mammals, fish, reptiles, plants, invertebrates. Insect populations in many regions of the world have declined by 70 to 80% over the last several decades. Freshwater species are disappearing at rates higher than terrestrial or marine species. The world's wild vertebrate populations have declined by an average of 69% since 1970. These numbers are already significant, but they are the beginning of a process, not its conclusion. The extinctions we have already caused are committed. The extinctions driven by the climate change we have already locked in are committed. The extinctions that will result from habitat destruction already underway are committed. The final magnitude of what we are doing to the biodiversity of this planet will not be known for centuries and will not be fully visible in the fossil record for millions of years. But it will be visible. It will be one of the clearest geological signals in the record for hundreds of millions of years. A sudden, global, rapid collapse of biodiversity in sediment from a specific layer on every continent in every ocean. Above that layer, a different world, impoverished in species, dominated by generalist opportunists. Visual. Comparison of a pre-industrial fossil layer with a post-industrial projection showing the diversity collapse. Then the same kind of comparison used to illustrate the KPG boundary and the Permian-Triassic boundary, placing our extinction event in company with the most dramatic moments in the history of life. Let us compile the complete inventory of what the geological record of our civilization will contain and how long each signal will persist. The carbon isotope excursion, globally distributed in marine sediment, will persist for tens to hundreds of millions of years. Though its amplitude will decrease with time, as diagenesis and compaction alter the sediment, detectable with current analytical methods across the entire archive of marine sediment from our era. The mass extinction signature will persist in the fossil record for hundreds of millions of years. The sudden collapse and restructuring of biodiversity at our stratigraphic horizon will be one of the most recognizable events in the history of life, visible from any well-preserved sedimentary sequence. The radioactive layer, globally distributed through atmospheric deposition from nuclear weapons testing. Cesium-137, half-life 30 years. Plutonium-239, 24,000 years. The layer itself and the anomalous isotope ratios it created will be detectable for millions of years in well-preserved sediment. The plastic and synthetic chemical layer, distributed in marine and terrestrial sediment globally. Persistence uncertain at millions of years timescales. Complex polymers will degrade, but distinctive organic compounds may leave detectable traces for longer than most current estimates suggest. The nitrogen signature, unprecedented quantities of reactive nitrogen compounds from industrial agriculture, have been deposited in sediment globally, creating an anomalous nitrogen isotope signature that will be detectable for millions of years. The heavy metal signature, atmospheric dispersal of lead, mercury, arsenic, cadmium, and other heavy metals from industrial processes has created a globally distributed geochemical anomaly. The lead signal in particular, from leaded gasoline, is sharp, global, and temporally precise, spanning roughly 1920 to 1985. The aluminum anomaly, as discussed, the unprecedented presence of pure metallic aluminum in sediment from our era, is a signature with no natural equivalent. The concrete horizon, the total mass of concrete humanity, has produced now rivals the total mass of all living plants on Earth. Structures that become incorporated into coastal or lacustrine sediments will leave distinctive mineral signatures detectable in the geological record. Collectively, these signals form a package, a fingerprint, not of any single event or any single process, but of a civilization, a species that discovered how to unlock ancient energy, that remade the surface of the planet, that drove thousands of other species to extinction, and that altered the chemistry of the atmosphere, the oceans, and the land. Future geologists will find this fingerprint. The question is whether they will recognize what made it. Let us go forward rather than back. 100 million years from now. A hypothetical future geologist, whatever that means, whatever species or intelligence is doing the geology, examines a sediment core from what was once the floor of the Atlantic Ocean. They notice several things in sequence. The carbon isotope record shows a sharp negative excursion, beginning gradually and then accelerating. A period of perhaps 500 years in which organic carbon was injected into the atmosphere at a rate that has no precise natural analog in the surrounding record. The biodiversity record shows a collapse at the same stratigraphic horizon. Below it, diverse assemblages of marine foraminifera, mollusks, fish, and other organisms. Above it, dramatically reduced diversity, with dominance by a handful of opportunist taxa, The pattern is identical to, though distinct in its magnitude from, the great extinctions they have already catalogued from other boundaries. They find the chemical signatures, unusual heavy metal concentrations, nitrogen anomalies, potentially the organic remnants of synthetic compounds. They find the isotopic anomalies from nuclear activity. They find the aluminum anomalies. And then they must decide what caused this. They have several hypotheses available. A large volcanic episode, like the Siberian traps, can produce carbon isotope excursions and biodiversity collapse, though the known Siberian traps event from 252 million years ago looks somewhat different in its carbon signature and its spatial pattern. An asteroid impact can cause biodiversity collapse, but typically shows an iridium anomaly and shocked quartz, and the carbon excursion pattern is different. A large methane release from the ocean floor can produce organic carbon-depleted carbon-13 signatures and warming. The PETM, which they have also catalogued, shows this pattern. But the PETM lacks the novel geochemical signatures, the synthetic organics, the aluminum, the particular pattern of heavy metals that appear in this layer. This layer is different. It is simultaneously familiar, carbon excursion, extinction, temperature spike, and anomalous in ways that do not fit any category they have previously encountered. What do they conclude? This is the heart of the Silurian Hypothesis, inverted. We asked, if a previous civilization existed, would we recognize its traces? The answer, Frank and Schmidt concluded, is probably not, unless we were specifically looking for them with methods designed to find them. Now we ask the parallel question. If a future intelligence examined our traces, would they recognize them as the products of a technological civilization? The answer is not necessarily, not automatically, not without the conceptual framework that allows them to ask the question in the first place. If they have encountered other technologically active planets, through direct exploration, through remote sensing, through the development of a science of civilizational detection, then yes, they may have a catalog of what technological activity looks like in the geological record. They may have exactly the suite of tests that Frank and Schmidt proposed, but applied in reverse, looking for artificial signals in ancient rock. But if they are the first intelligence to develop that framework, if they are where we were when Frank and Schmidt wrote their paper, then they will try to explain the anomalous layer with natural mechanisms. They will iterate through volcanic explanations, impact explanations, natural methane release explanations. They will find that none quite fits. They will publish papers debating the anomalies. The explanation, intelligence, may be the last hypothesis they consider, because the methodological bias that Frank and Schmidt identified in our approach to the past applies equally in any direction. We look for natural explanations because natural explanations are usually correct. Intelligence in the cosmos may be rare. The prior probability of finding evidence of intelligence in any random geological layer is low. Occam's razor cuts toward natural explanations, unless you already know that intelligence exists and leaves detectable traces, unless you have already encountered it, either in the past or in the present. We know intelligence exists. We are it. And we are about to leave the clearest evidence of intelligence that this planet has ever produced. Possibly the clearest evidence that will exist in the geological record for hundreds of millions of years to come. The Silurian Hypothesis began as a thought experiment, a diagnostic tool to probe the limits of geological detection. It has led us through 4.5 billion years of Earth history, through the machinery of geological erasure, through the chemical ghost of the PETM, through the plastic and radioactive fingerprints of our industrial civilization, through the edge of human memory and the silence beyond it. And it ends here. Not with an answer to the question of whether civilizations preceded us. We probably cannot know with current methods, and we are probably alone in Earth's history. But with a question directed at ourselves, we are currently the first, or the only, technological civilization this planet has produced. Everything we do from this point forward writes itself into the record that will outlast us. The carbon we release will be in the sediment for tens of millions of years. The species we drive to extinction will be absent from the record for hundreds of millions of years. The radioactive isotopes are already there. The plastics are already there. The chemical signatures are already there. The question is not whether we will leave a mark. The question is what that mark will say. Right now, the mark we are leaving reads like an extinction event, like a mass die-off, like the boundary between one world and a diminished version of it, like the thin compressed layer that future paleontologists will examine and label. Here, something catastrophic happened. But the record is not complete. The record is still being written. Every decision made today about energy, about agriculture, about land use, about what we choose to preserve and what we allow to disappear, every one of those decisions is an entry in the geological archive, a choice about what story the stone will tell. There is a dimension to the Silurian Hypothesis that Frank and Schmidt explored in their paper, but that is worth making explicit. We are currently engaged in the search for extraterrestrial intelligence, and more broadly, for evidence of life beyond Earth. We scan the atmospheres of distant exoplanets for chemical biosignatures, oxygen, methane, water vapor, ozone, that would indicate biological activity. We listen for radio signals from technological civilizations. We send probes to Mars to look for microbial life, present or past. All of these searches rest on an assumption that we know what we are looking for, that we understand what evidence of life, and especially of technological civilization, looks like from a distance, across time. The Silurian Hypothesis challenges that assumption. If we cannot be certain of detecting a previous industrial civilization on our own planet, in our own geological record, using our most sophisticated analytical tools, how confident should we be about detecting one across interstellar distances? The carbon isotope excursion, the mass extinction signature, the chemical anomalies that define our era, these are observable from Earth. But from a distance, from another star system, observing our planet remotely, the signals are attenuated by distance, mixed with noise, filtered through the uncertainty of remote sensing. The silence we hear from the universe, the absence of detectable signals from other technological civilizations, the phenomenon known as the Fermi paradox, might not reflect the absence of civilization. It might reflect the limits of our methods. and our inability to recognize signals we do not know how to look for. The detection gap that the Silurian Hypothesis reveals is not just a problem for Earth's past. It is a problem for the entire project of understanding whether intelligence is common or rare in the cosmos. We are building the first generation of the tools we need. The James Webb Space Telescope is already detecting chemical signatures in the atmospheres of planets tens of light years away. Future observatories will improve on this by orders of magnitude. The question of whether any of those chemical signatures represent a technologically perturbed atmosphere, an Anthropocene equivalent on another world, is becoming scientifically tractable. But we need to know what we are looking for. And we only know what we are looking for by understanding what we ourselves are doing to our own world, and what the record of that activity looks like in the deep geological archive. 4.5 billion years. Let that settle. The Earth was here, doing what planets do, forming, cooling, being pelted by debris, developing a thin film of chemistry that eventually became alive, for a length of time that makes our entire existence as a species feel like a rounding error. And in the last fraction of a second of that time, in the geological instant that is our industrial civilization, we have altered the course of life on this planet in ways that will be visible in the rock for the next 100 million years. We did not mean to. We were not acting with geological intent. We were building and burning and growing because those things met the needs of living people in living moments. We were not thinking about what the sediment layers would look like in 50 million years, but the sediment does not care about our intent. It records what happened, not why. The carbon is in the atmosphere, whether it got there through human industrial activity or through volcanic eruption. The species are extinct, whether they were killed by an industrial civilization or by an asteroid. The record is what it is. This is the image the Silurian Hypothesis leaves us with, not the image of a previous civilization, buried and forgotten, its ruins lying undiscovered beneath our feet. That may or may not be real. We probably cannot know. But the image of our own civilization, from the outside, from the perspective of the rock, compressed into a thin layer, marked by carbon and extinction and the novel chemistry of our industrial output. Legible to whoever or whatever has the tools to read it for 100 million years. What does that layer say about us? What will it say? The record is still being written. The stone is still accepting new entries. The choices we make today about energy, about what we protect and what we sacrifice, about how we respond to the evidence of what we are doing to the living systems of this planet, will be part of that record. We will leave a mark. We already have. The question is what kind of mark it will be. The sand falls through the fingers again, slowly, each grain a year, each year a choice. We began this journey on a beach at night, watching time fall through our hands. We have followed it down into the dark, past the edge of human memory, past the edge of written history, past the youngest layers of sediment, and into the deep geological archive where only chemistry and physics speak. What we found there was not a lost civilization, not the ruins of a forgotten intelligence, not a definitive answer to the question we began with. What we found was a mirror. In the deepest past of this planet, in the chemical anomalies of the Paleocene-Eocene, in the erased surface of an Earth that has been recycling its crust for billions of years, in the silence that extends back before the oldest fossil, before the oldest stone tool, before the oldest memory, we found ourselves. We found the question that our civilization is currently answering in real time. Not, were we the first, but what will we become? Not, did something come before, but what will come after? Not, is there a previous civilization hidden in the rock, but what is the civilization we are currently hiding in the rock, the one future geologists will excavate from the sediment of our era, going to tell them about who we were and what we chose to do with the extraordinary, vanishingly brief moment that was ours. The beach stretches back into darkness, and the sand still falls, and the question is still open. Fade to black.